Spinning tops exhibit torque-induced gyroscopic precession, which causes the top to wobble as opposed to tipping over. In this video, let's explore this precession thoroughly by using the simplest, easiest to diagram example, a spinning bike wheel on a rope. If we understand this classic example, we understand the top, along with any other body which experiences torque-induced precession. In order to get a full understanding of this system, we're going to break this video into three parts. First, I want us to recall Newton's second law for systems of particles, and see that it provides an accurate, yet incomplete description of the gyroscope. This will next motivate us to instead look at a small subsystem within the gyroscope, say some small chunk in the bike wheel, and apply Newton's second law there to help us intuit more about this complex behavior. And finally, we'll realize how nice it would be to explore the system with simple macroscopic principles as opposed to worrying about everything on the microscopic level. We'll introduce torque and angular momentum into the picture and ultimately derive the formula for precessional velocity. Alright, so here I've drawn out a very simplified side profile of this spinning bike wheel gyroscope. Right, we make the wheel spin with some angular velocity, little omega, and we observe that the gyroscope precesses with this angular velocity, capital omega. Alright, so what does Newton's second law when we apply it to systems of particles tell us about this? Right, and so if I call the mass of my gyroscope capital M, and say its center of mass is like over here, then I have the force of gravity, right, mg, and I have my tension force, right, from this rope here, T, right? And so what does the Newtonian picture say when you deal with a system of particles, right? We say that sigma F external is going to be equal to, right, this tension force plus this gravitational force, right? And then we say this all sigma F equals ma, but m times the acceleration of what? It's the acceleration of the center of mass point of your system of particles. This is telling you about the acceleration of one point, the center of mass of that entire system. In other words, it tells you nothing about the acceleration of, perhaps some ith particle in the bike wheel, right? And so I can break this tension up into its components, call this T up, and then this inward component, which I'm going to call T in. And so we can write out two equations. First, in the vertical direction, I'm going to have T up minus mg is going to have to be equal to 0, right? Which is just a statement that these forces are going to have to cancel so that this center of mass isn't moving up or down. All right, as for T in, right, if I have this precessional velocity, capital omega, what's this point going to do? It's going to traverse, in a circle, right? It's going to traverse in a circle, right? And anytime that you have uniform circular motion, you need some sort of centripetal force. That's going to be provided by T in. So we have that T in is going to be providing your centripetal force F sub c, which is going to be equal to m omega squared times r, right? Where r is going to be the radius of that circular motion, right? And so indeed, the fact that you need this inward centripetal force means that this rope here is going to have to be at a slight angle theta. Generally, this angle is very small, but indeed there are ways to solve for it, if you have a better understanding of this precessional velocity, which is what we're going to cover in the next parts of this video. Alright, but really that's it. When applying Newton's second law to this complicated system, that's really all that it says. It doesn't care about all these details that we have all these spinning particles in the bike wheel or any of the complexities like that. It says, look, this system can be pactified into one point, the center of mass, and that center of mass point is going to follow some rules based on the net external forces acting on that entire system. Alright, but it's always important to remember, and it's also comforting that, no matter how complicated these systems of particles get, your classic Newtonian interpretation of that system of particles of just compactifying everything down to one center of mass point, that's always going to work. And of course, that simplification is still very powerful. It's just not enough for us to get an intuition of what's happening with the gyroscope here. Alright, so next, maybe instead of looking at the total system of the gyroscope, if instead we zoom in and look at small little subsystems, right, some little chunks or like particles on the wheel, then we might be able to get more intuition to what's going on here. Okay, and I've got the two cases here. First, the bike wheel isn't spinning at all, and then we introduce spin into the bike wheel, right? And in the first case here, I wrote the center of mass in red, right? We're going to have mg acting down. The effect, in case one is going to be very obvious, which is, this bike wheel is just going to act kind of like a pendulum, right? It's going to start swinging downwards, right? But even in this case, where the bike wheel is swinging down, think about what's actually happening to those top and bottom particles for a second. Just because gravity, the net external force, is going down, these top and bottom particles aren't necessarily just moving up and down at all. Look, this top particle, it's getting pushed outwards a little bit, and this bottom particle is getting pushed inwards a little bit. And of course, we see that they're also moving up and down because I'm drawing a finite change in the wheel. But you can imagine that at the very beginning of the swing, right, these guys are actually just getting pushed outwards and inwards. Alright, so we see that, right? I'm going to call this F sub j, right? The actual forces on these jth particles aren't matching the actual direction of our gravitational force, right? And these are the subtleties that you have to start thinking about with systems of particles, right? Just because I have this net external force acting on my system, that's not necessarily telling me about the forces on, again, like the jth particle of the system, right? These are the things that we kind of black bag and just ignore when we make assumptions and constraints about the problem, like saying things like, we have a rigid body, right? In general, we don't need to worry about the internal forces and all of that nonsense that makes the rigid body rigid. We just go with that. Alright, but now seeing the forces that are pointing outwards and inwards, I think we're going to have a much easier time understanding why this bike wheel is going to precess the way that it does, right? So if I go and I draw these particles again at the top and the bottom of the wheel, by the way, if the wheel is spinning at me, what's the direction of the tangent velocities of these particles at the top and the bottom? Well, the particle at the top is going to have a velocity coming towards me, which you indicate with a little dot, right? And the particle at the bottom of the wheel is going to move with a velocity into the page, which we indicate with a little x. Top particles coming at me, bottom particles going away from me. All right, and again, we have some force pointing this way and some force pointing this way. Right, and so what do perpendicular forces do to velocity, right? Perpendicular forces change the direction of your velocity, right? All right, so I'm going to write this out in like an infinitesimal version for these particles, okay? Just to really hit this home. So if I have a top-down view, I put a little eyeball down and it's, looking top down such that it sees the top particle, okay? It's going to see the top particle moving downwards now. So here's V and here is F, right? And of course, the opposite, it's going to see for the bottom particle, it's going to see it with this F here and moving upwards. Then I want us to imagine what's happening to these velocities in an infinitesimal time dt here. So what's really happening in an infinitesimal time dt here is these forces are delivering very, very tiny little baby accelerations dA, right, to each of these particles. So that's what these forces are actually doing to these particles, right? they're changing the direction, not the magnitude of the velocities, right? And so what orientation is the bike wheel going to have to be in, with this configuration of velocities, right? That's going to have the bike wheel, all right? I'm just going to go ahead and draw out the answer here on the bottom. You can do the flip these pictures around in your brain to go from top-down view back to this view, right? But then this velocity here, right? That's going to be just like this. Here's v prime, and this velocity down here is going to be just like this. Here is v prime, right? And of course this is attached to the string, and then here's the ceiling here, right? My bike wheel started in this top position here, and now it's precessed a tiny bit into the page, right? Does that make sense? So the direction, which we can actually deduce from this kind of intuitive picture here, is going to be in this direction, right? And remember, I'm drawing these like they're static images, right? But these are infinitesimal steps. So every time the bike wheel starts precessing a little bit, right? Now the direction of these forces change again, right? And so then we can draw another picture, and we can keep imagining the velocities going tick, 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 right? And rotating around as this gyroscope gyrates. Okay, but even though I use this to give us some intuition, I'm still being a little simplistic in this description here, right? Because I'm not really including all of the internal forces that are acting on these particles, right? Even to the level of to have this particle spinning on this bike wheel, right? There has to be a centripetal force acting on it, F sub c here, right? I'm not including that, right? Which is why I've deceived you into thinking that, that these particles at the top and the bottom here are the same particles at the top and the bottom here. That's not true, right? There's spinning happening here. All right, and we could start trying to add back in more and more internal forces, to get a better and better picture of what's going on. But that brings me to my next point, which is that for complicated systems, we don't want to analyze things using all these internal microscopic forces. That's going to make our picture way too messy, way too quick. Think about how many particles are actually in a bike wheel. We're talking about an Avogadro's number of particles. It's impossible to do meaningful calculations on, such a large system. So we don't want to look at things microscopically. We want to come up with simple macroscopic parameters to describe our system. All right, and so finally we're going to use macroscopic parameters, aka torque and angular momentum, in order to very succinctly and cleanly explain the gyroscope. And specifically, we're going to derive the precessional velocity, which I'm going to call capital omega of this system. So our goal is to derive capital omega using torque and angular momentum. So the first thing that we want to do in order to derive this precessional velocity is we want to define the angular momentum due to the spin of the bike wheel, due to this little omega here. All right, and so it turns out that you can actually write out angular velocities like vectors, okay? So I can take this little omega and write it as a vector pointing outward, right? Where the magnitude of this vector is the size of this angular velocity, right? And for the direction of this angular velocity vector, we use the right-hand rule. Right, so we can very clearly see the right-hand rule demonstrated pictorially here. If we curl our fingers of our right hand in the direction of this angular velocity little omega, then our thumb is going to point out in the direction of the angular velocity vector. And so from here, it's very easy to write out the angular momentum vector. Our angular momentum due to the spin of this bike wheel here is going to be equal to I sub s times this omega vector, okay? And so it is going to point parallel to this omega vector. Here is L sub s. Okay, and we know that there's going to be a torque acting on this system due to gravity, and we're going to see what that torque actually does to L sub s here. Okay, so what do I mean by that? We know that we're going to have a force due to gravity, right? mg here acting on our center of mass, and that's going to provide a torque, right? If I go ahead and put my origin, I'll call this O here, I'm putting it at the point that this, that this system is going to be precessing about, then the torque about O is simply going to be equal to mg times r center of mass. Now, torque, of course, is a vector. I've only written out the magnitude of my torque vector. In order to figure out the direction of my torque vector, we're going to have to use the right-hand rule again, right? So the general definition for torque is going to be r cross F. So in this case, r is r sub center of mass, and our force is gravity mg here. Okay, and so if you curl the fingers of your right hand, starting from the first vector in the cross product, and curl them towards the tip of the second vector in the cross product, keeping the origin of the two vectors at the same point, then your thumb is again going to point in the direction of the torque vector. Okay, and so if you do that with your right hand, try it with this picture, you're going to see that my perspective might be a little bit jank here with this thumb, but it's going to be pointing into the page. All right, so now let me go ahead and go up to this top diagram here and indicate that we have a torque, which is going to be pointing into the page. Alright, this diagram here is getting pretty busy, but that's okay. All that we really need to worry about are the torque and angular momentum right now. And in fact, we're going to imagine somebody looking at this, from a top-down point of view. So if somebody's looking down at this torque and angular momentum, alright, so in this top-down view, we're going to have our angular momentum vector, L sub s, pointing outwards, and we're going to have our torque vector perpendicular to that. Alright, so the next thing that I want us to imagine here is what is this torque actually going to do to my angular momentum in some time dt. So imagine that an infinitesimal amount of time goes by dt. So my angular momentum, right, is simply going to change directions. So if I have L sub s here, in some time at dt, this torque here is going to offer a very small change dl. All right, and we can add these two vectors together and we're going to have ls prime here. All right, so do you see what's happening? If I keep taking this limit, right, this dl is going to get smaller and smaller. What's happening is that ls prime is really just changing direction, all right? And specifically, it's changing the direction here by some little amount, which I'm going to call d theta, right? And so now we can write out dl is going to be equal to L sub s d theta, right? Do you see exactly what I'm doing here? So we have this vector here, right, which is essentially a little arc between ls and ls prime, right? And if we want to get that arc length, we can do that simply by taking the distance to the arc, which is ls here, times the angle subtended by the arc d theta. And that's going to tell us this little arc length here, which is the same thing as the size of the dl vector. All right? And remember, this process is happening in a small infinitesimal amount of time, dt. So this is per some dt. Right, and so now the key thing to see here is, remember, we were doing all this picturing in a top-down view. So if you take this picture here and you rotate it 90 degrees so that it's back in this plane here, right, then you're immediately going to see that this d theta dt here, right, what angular velocity is that? Oh, that's this capital omega. That's our precessional velocity, capital omega. Right, and remember this dl dt here, right, this rate of change of my angular momentum, right, what was that caused by? That was caused by my torque, tau, right, which we already solved for. That's mgr, right? And by the way, what is ls going to be? Well, oh my goodness, look, we already have that too. It's going to be this is omega here, right? So let's plug everything in. We have mgr, center of mass, is going to be equal to I sub s omega times capital omega, all right? And so now we can just write out our precessional velocity, capital omega, and there we go. We have this expression here for the precessional velocity of our gyroscope. right? So as long as you give me some basic physical parameters of this bike wheel here and tell me how fast it's spinning, right, then you're going to be able to write out the precessional velocity. How much is this system going to precess? All right, so I'm going to go ahead and end this video here. Hopefully this was a nice kind of walkthrough. There's so many more perspectives that you can put on the gyroscopic system, but these are kind of three key perspectives that I think give you a very complete view of what's happening. Before I end the video, I do want to say thank you so much to everyone who subscribed to this channel so far. Hopefully you enjoyed this little walkthrough on gyroscopes. But anyways, other than that, thank you so much for watching.